Може и вратата да оставим отворена, не е проблем.
Мисля, че трябва да бъдеш някъде микрофона да може да се включи.
Да, ако искаш, може да седиш направо с това, когато...
Hello. So, I would like to open the Viva of Nikolay Nikolov, who is a graduate of the Sofia University, applied mathematics in 2013. Then he successfully defends his master thesis in the direction of mathematical modeling of economics with supervisor Professor Nikolov. And now we are here to see his PhD work and to have discussion on it. We'll have Professor Krishna from Canada, from McMaster, if I'm not mistaken, who will be joining us via Skype, so the discussion will be in English and we'll be hearing from him when the time for discussion comes. So I believe that this is the general rule. Otherwise, I would say that probably not the moment now, but just say that Nikolay satisfies all the criteria for award of PhD, but we'll have the option to discuss this later. The procedure will be the following. So Nikolay is going to have 25 minutes for his presentation. Then we'll present our long reports and short reports, because there are two types of reports that we have prepared. Then we'll have, everyone will have the opportunity to ask questions, but in principle, we start with the scientific committee who asks questions and makes some statements about his impressions about the work of Nikolay. Then also the members of the public can also ask to the scientific committee questions or maybe say some words about Nikolay. And then we'll have to vote in the end about the outcome of this Viva. And then we'll present the result and this will be the end of the Viva. So if I'm a little bit wrong in some of the procedure, it's my first time. So.
Thank you. So the thesis in general considers the problem of analyzing and modeling rank data. Rank data is commonly arise in situations where n objects or items needs to be ordered by some criteria. Examples of rank data can be found in voting and elections where they originally came from, or in psychology, biology, market research, and many other fields. The rank data can be collected directly by some preferences or can be by some transformation of continuous or discrete variables in non-parametric analysis. The thesis is structured in 5 chapters. Okay, so today I'll shortly present the first and second chapter and fourth chapter, while the results from chapters 2, 3, and 5 have already been presented on the national seminar here. In general, a complete ranking of n items can be viewed as a permutation in the permutation group Sn generated by the first n integers, where its ith component is the rank of the ith item. The corresponding ordering is given by the inverse permutation, and for which the jth component is the item assigned with rank j. Okay, here's one classical example of arranging books on a shelf. Let's suppose we have 6 books labeled with the letters from A to F, and then for the ranking 6, 4, 5, 1, 2, 3, this means that the first book is on the 6th place, the second book is on the 4th place, and so on, and the corresponding ordering on the shelf is given here. It is possible to observe only part of this ranking, so these kind of data are called partial rankings or partially ranked data. However, main focus of the thesis is on complete rankings. In order to get some structure in the rank data, we should first define a distance on the permutation group Sn. So a distance is a function from two permutations to the real numbers that satisfies the following three conditions. And if furthermore it satisfies the triangle inequality, then we say that this distance is a metric on Sn. Here are 8 of the most commonly used metrics on permutations. I will not discuss them in details. I'll just say that the first three, Spearman's rho, Spearman's foot rule, and Chebyshev metric, are equivalent to L1, L2, and max norm, while the main goal of the thesis is to study the statistical properties of Lie distance, since most of the applications of Lie distance have been in coding theory, where it's originally proposed. Here are some important properties of distances on permutations. The first one is we say that the distance is Hövding distance. It can be decomposed. The second one, we say a distance is right invariant, or also called label invariant, if it doesn't change, if we change the labels of the items, for example, the labels of the books in the previous slides. And we say the distance is left invariant if it's not changing if we change the values of the ranks, not the order of the ranks, but just the values of the ranks. From the 8 listed distances before, all are metrics and right invariant, and only Cayley distance and Hamming distance are left invariant, and they are called also bi-invariant. Let's now consider a random variable constructed in the following way. The random variable d is the distance between some uniformly chosen permutation from the Sn and some fixed permutation pi 0. Then if the distance d is right invariant, we can rewrite d as the distance between the identity permutation and some uniformly chosen permutation from Sn. Or in other words, the distribution of d does not depend on the choice of the fixed permutation pi 0. This random variable finds various applications in models for rank data. So the first goal of the thesis was to study the properties of DL, the random variable induced by Lie distance. So the random variable DL can written as the distance between the Lie distance between the identity permutation and some uniformly chosen permutation pi can be linearly decomposed, and here the quantities Cn have a nice interpretation in terms of graph theory. So let's say that G is a simple graph with nodes the integers from 1 to n and edges connecting two consecutive integers. Then the quantity Cnij is just the minimum distance over G between the nodes I and J. Here is an illustration. Let's first consider the case when n is even and fix the node I, and let J, the node J, be some arbitrary. Then this quantity Cnij is given on the left graph as number next to the dotted red line, and what we can see is that this quantity is from 0 when j equals I to n over 2 when j is I plus n over 2. When n is odd, this quantity is from 0 to n minus 1 over 2 for 2 nodes. Okay, so we can write that the random variable dl is between 0 and n times the integer part of n over 2. Here the square brackets are the integer part. And the lower limit is reached for the identity permutation, while the upper limit, when n is even, is reached only for the opposite permutation to the identity, and it is constructed from the identity by taking the first n over 2 integers and moving them to the end of the permutation. In a similar way, we can construct the opposite permutations for the case when n is odd, but here we'll have two opposite permutations. Okay, so here is in our example, if we consider the identity ranking, which corresponds to the ordering A, B, C, D, E, F, then the opposite ranking based on Lie distance is constructed by taking the first three books and moving them at the end, while this quite differs from the opposite rankings based on some more commonly used metrics such as Spearman's foot rule, Spearman's row, and Kendall's tau, where the opposite ranking is just the reverse ordering. In order to derive some asymptotic properties of the random variable DL, we make use of the Hoeffding's combinatorial central limit theorem, which states that if we have a random variable induced by a Hoeffding distance with quantities an, then its expected value can be written in the following way, and its variance is expressed by these summations, where the quantities bn are defined here. Furthermore, if this limit condition is satisfied, then the standardized random variable d converges in distribution to a standard normal random variable. In the case of Lie distance, the quantities a and bn are given here, and the expected value and the variance, and the expressions for the expected value and the variance are given here. Furthermore, it turns out that the condition in Hoeffding's theorem is satisfied for Lie distance, or in other words, the random variable DL is asymptotically normal. However, the random variable DL can only take even values when n is even. So if you want to apply the normal approximation of the probability mass function, we need to take the random variable integer part of DL over 2. And then the normal fit for the probability mass function in the case when n is from 7 to 10 are given below. As we see, when n increases, the fit gets better, the normal approximation gets better. Okay, so in chapter 2, models for rank data are considered. Let's say that we have, I'm not sure here it is visible. Let's suppose that we have a random sample of n complete rankings. So each observation is a complete ranking. One possible way to define a model over such data is to give a probability distribution over all possible permutations, and one of the most commonly used models is the Mallows model, or also known the distance-based model, for which the probability of observing a given permutation pi depends exponentially on a real parameter theta, distance on Sn, fixed model ranking pi 0, and a normalizing constant psi. The exponential family and was first proposed by Mallows and later generalized by Flinger, Vedulucci, and Diaconis. Here is an example. Of the probability distribution when the Mallows model is based on Kendall's tau, and the fixed ranking pi 0 is model ranking, or this corresponds to negative values of the real parameter theta. And in this example, n equals 5, so we have 120 possible permutations of 5 elements, and here here are given the probabilities of the model ranking for 3 values of theta. And what we can see is that if we go away from the model ranking pi 0 in terms of Kendall's tau distance, for more general models are considered. In chapter 3, some clustering procedures for rank data are described, and the k-means clustering based on Lie distance is studied in more details. And now I'll present the results of chapter 4, which which considers the malus models as an alternative model in the framework of ranked set sampling. Ranked set sampling is a sampling procedure which is more efficient in situations where the random variable of interest is difficult to be measured. This means that the actual measurements of the random variable of interest are costly or time-consuming. To obtain a one cycle ranked set sample of size k, first we need to draw a set of k objects, but not measuring them. And after that, we order them from the smallest to the largest by some judgment criteria, judgment ranking criteria. Here, the random variable of interest is continuous and denoted by x. So the order of the first set is given here, and we take to measurement only the smallest observation in the first set. Here it is the collected measurement is denoted with x1 in square brackets. After that, we draw another set of k objects and order them by some judgment ranking criteria from the smallest to the largest, but this time we are taking for measurements only the second smallest observation and denote it with x2. Take for measurements only the largest observation and denote it with xk. In this way, from k squared objects, we have measured only k of them and obtain the one cycle ranked set sample. If we repeat this procedure n times, we obtain an n cycle ranked set sample. For simplicity, here I'll present the results only for one cycle sample, while in the thesis they are generalized for the n cycle sample. Here is an example considered by Murray et al., who studied the effect of force prayer settings on the amount of deposit on apple leaves. So the random variable of interest in this study was the amount of spray deposit, which was measured as the percentage of leaf surface covered with deposit. Of course, this measurement is precise and it's difficult, takes a lot of time. So they applied the ranked set sample procedure with for k equals 5, so for 5 objects, in this case leaves. So so how the data was collected? First, they sprayed the apple leaves with some deposit that can be seen under UV light. After that, after that, they randomly selected 5 leaves and ordered them from the leaf with the smallest amount of spray deposit to the largest under UV light. So the judgment ranking criteria was the visual ordering under UV light. And in the first set of 5 leaves, they measured the smallest, the one with the smallest amount of spray. And in this case, it turns out that it's 0.3% of the leaf surface. After that, they draw another 5 apple leaves, order them visually under UV light, and take for measurements, for precise measurement, only the second leaf, and it turns out that it's 2.8% covered with deposit. So the complete sample is given here for the 5 steps in this cycle. And what we should ask is, does we have a perfect ranking, in the sense that the actual measurements highly depend on the choice of our apple leaves to be measured. So we are asking, do we have a perfect ordering under UV light? So is this judgment ranking criteria are perfect? So correctly choose to measure the smallest leaf here and so on, or we made some mistakes, or in this case we say that we have imperfect ranking. Okay, so if we take our collected measurements, and if we take their average value, then it turns out that this is an estimator for the mean of the random variable of interest x, and this estimator is more efficient than the standard average based on a simple random sample of size k, in terms that the variance of this estimator is less than the variance of the estimator based on the simple random sample of size k. A similar property is true for the estimator of the variance, and in general the ranked set sample can be applied in various statistical procedures such as hypothesis testing, estimation of parameters, or regression analysis, and etc. However, the efficiency of the ranked set sampling procedure highly depends on the ranking abilities, or in other words, do we have a perfect ranking or not? So Lee and Krishna proposed a non-parametric approach for testing the hypothesis of perfect ranking. They used the ordered ranked set sample, which is obtained just by arranging the collected measurements from the smallest to the largest, which of course corresponds to a permutation. Since our variable of interest is continuous, we don't have ties, and this corresponds to a complete permutation of the integers from 1 to k, and here it is denoted with I1, I2, Ik, the permutation. And they showed that the probability of observing a given permutation under the assumption of perfect ranking can be expressed in the following way. In our example, the observed permutation corresponding to the ordered ranked set sample is 1, 2, 4, 5, 3, which has probability under perfect ranking approximately 2%. Although if we have a perfect ranking, we would expect to have a strictly increasing values in our ranked set sample. It is not always the case. It is possible to have a perfect ranking, but here the values will not be in an increasing order. So to specify the model for imperfect ranking, we should specify the probability with which the jth order statistics is judged as having rank I. So these are probability when I is not equal to j. This probability is also called the error probability. If we take these probabilities Pij for I and j from 1 to k, we form a square matrix that is a double stochastic matrix, and it is called error probability matrix. So one such matrix defines a model for imperfect ranking, and Lee and Krishna showed that under a given matrix, error probability matrix, the probability of observing a given permutation in the ordered ranked set sample can be expressed by this formula in this fashion, where here the probabilities on the right are under perfect ranking, and under the assumption of perfect ranking, while the probabilities in the product are from the error probability matrix. So to test the hypothesis of perfect ranking, Lee and Krishna proposed 3 test statistics which are based on the distances between the observed permutation and the identity permutation, which is associated with the perfect ranking. So the 3 statistics, N, S, and A, are based on Kendall's tau, on Spearman's foot rule, and on Spearman's rho and Spearman's foot rule. So the hypothesis of perfect ranking is rejected when the values of these statistics are too large, since the perfect ranking is associated with the identity permutation. And the distributions under the null hypothesis of these 3 statistics can be calculated by using the formulas shown before on the previous slides. Okay, so in chapter 4 we propose the malus models as an alternative model for imperfect ranking. And in this case, we should take pi 0 to be the identity, since the goal of the judgment ranking criteria is to perfectly order the observations in each set. While so this to be a model ranking, we should take the values of theta to be less than 0. And then the elements of the error probability matrix, here it is denoted with Q, can be written in the following way, where the summation here is taken over all possible permutations such that their jth component equals I, or the jth ordered statistic is judged as having rank I. What we can notice is that when theta is 0, this corresponds to the uniform model, and all elements of the error probability matrix are equal to 1 over k, or this corresponds to just randomly ordering the objects in each set. So in this case, the ranked set sample does not perform better than the simple random sample. If, however, theta goes to minus infinity, then the error probability matrix converges to the identity matrix, which is associated with perfect ranking. So we can say that parameter theta actually measures the ranking abilities of the judgment criteria. Here is an example based on Kendall's tau. Based on malus model induced by Kendall's tau for k equals 5 and theta equals minus 1/2. What we can see here, the first value is that the smallest number in each set is correctly judged or correctly taken to measurement in the first set in approximately 43%, not for a fixed parameter theta, but to a sequence of parameters that satisfy the following condition. Similar results are derived for Spearman's rho and for Spearman's and for Lie distance. In order to estimate the unknown parameter of our model, we should calculate the likelihood function, which is given in this way. So and we cannot find the maximum likelihood estimation of theta directly. So we make use of the EM algorithm. So we define the complete likelihood function based on the unobserved true rankings Z. Here Z1 is the true ranking of the first measured observation in the first set. So the EM algorithm is iterative algorithm that has two steps in each iteration. The first step is to find the expected value of the log likelihood function. And the second step is to find the argument that maximizes this quantity. We should take the expected value of the log likelihood function for a given initial approximation of the parameter theta. Here it is denoted with theta, while the reach some fixed number of iterations. If we go back to our example with the apple leaves and sprayer deposit on them, we already saw the values in the first cycle of the ranked set sample. Okay, and here is the corresponding ordered ranked set sample and the permutation. It turns out that the three values of the test statistics for the hypothesis of perfect ranking are insignificant. In other words, we cannot reject the hypothesis of perfect ranking in the first cycle. Similar results are true for the next four cycles. So in general here, however, these data are collected for a given setting for the sprayer, and these were for low volume settings. And by using the EM algorithm for a 5-cycle sample, we can estimate the unknown parameter in the Mallows model based on Spearman's foot rule, and it turns out that it is minus 0.49 approximately. And here is the corresponding error probability matrix. So we can use this error probability matrix to compare the judgment ranking abilities, or in this case the visual ordering under UV light, for the case for the low volume settings, and to compare them with another data which was collected for the high volume settings of the sprayer. It turns out that the estimated error probability matrices are significantly different, or we can conclude that the ranking abilities when in the high volume settings scenario are better, significantly better compared to the ranking abilities under UV light based on the low volume settings. In chapter 5, we considered the Critchwell's unified approach for constructing the rank test statistic for 2-sample location problem and applied to the lead distance, and the derived test statistics is compared to other rank test statistics for 2 samples. Here are some references for the presentation and the thesis. Here are the main contributions of the thesis and related publications. Thank you for your attention.
We have to proceed to the next step of our procedure, whereby the members of the scientific committee are going to present their short and long reports respectively. In principle, people have had at least 2 weeks of time to be acquainted with the material, so the standard procedure is that people just make a short overview of their comments, their suggestions and their opinion about the work. Of course, if they wish, they can read some parts of it, and also they have to present their decision whether they support the word of the title PhD or not. And afterwards, after we finish presenting these materials, I'll open for questions. So now we'll only discuss the reports. We'll start with the long reports, and I would invite Professor Balakrishna, who is one of the members of the jury and who also wrote a long and detailed report on the work of Nikolay, and that he presents his opinion and the content of his report. So.
Thank you. First of all, I want to. Can everybody hear me?
I hear, yes. Yes.
Okay. The reason I was asking is that when Nikolay was making presentation, about 25% of the time I could not hear. I think the connection was very poor. I kept getting a message saying the connection is poor. First of all, I want to thank everybody for including me in this evaluation process. I greatly enjoyed reading the thesis, and also I have had the pleasure of listening to Nikolay make presentation in a couple of conferences that I attended. I have written a long report, so I don't want to take too much time in reading over what I explained in thesis, but I want to make that the results established in the thesis are quite sound.
Okay. There is an interruption.
Okay, so I'll try to. Ами, освен да му напишем, че след малко пак ще му се обадим. Освен да му напишем, че след малко пак ще му се обадим. Ага. Ами, надявам се, че проблемът всъщност не е при нас. Да, и аз така мисля. Ами, ако искате, пробайте си вие. Че аз съм вашия път. Не, имаме го тук. Обаче не ми се случи проблем при нас, защото пък тук имам връзка с... Ама проблемът е следния, че ще ми се изгуби тази камера. Това не може да се изгуби. Ето, So this I can answer now, or
He can answer now.
yes. Can you hear me now? Can you hear me now?
That's what I was curious, because there has been some attempts made to the estimation of rho, and it looks to me, when I looked at your presentation now, that you have all the tools in order for you to assume a bivariate normal error specification and to do the EM algorithm for the likelihood estimation of rho. And this has never been attempted before. I have to say that you have developed the tools, which gives me this idea, because when Tao Li and I worked on this, I was thinking about it, but I never did it. But it looks like you have all the tools to do.
Yes, there is a relation between the parameter theta and the parameter rho in this bivariate normal model, and however, for the bivariate normal value, when rho goes to 1, we have perfect ranking, while here, when theta goes to minus infinity, we have perfect ranking. But I guess the estimation of the parameter rho can be done in a similar way by taking this complete likelihood function, right? Yes. Probably, but here there should be the error probability matrix based on this bivariate model. You don't see. Sorry.
I have two connected questions. Can Oh, sorry. You want to show me something?
Yeah, I want to show that this is the complete likelihood function, and here instead of the quantities q, we should take the quantities, the error probability elements of the model based on bivariant.
Bivariate normal, exactly.
Normal, yes.
I think that will be interesting because bivariate normal error specification is the one that commonly gets used in
Yes.
all the works of Doug Wolf and Omer Osterk and all these people who work on rank set sampling.
Yes, so thank you for the idea. I believe it is possible, but of course further studies should be made.
Another question, this is more of a information for my own benefit. In the model, that Mello's model that you look at, it is based on the parameter theta. And if I remember correctly, the parameter theta is equal to minus infinity, corresponds to the perfect ranking.
Exactly, yes.
Does this pose a problem in the parameterization of Mello's model? For example, one typically would do something like a construction of a confidence interval and see whether the parameter corresponding to perfect ranking gets included in the confidence interval or not.
Okay,
right?
Yes. Yeah.
And if theta is minus infinity, how does one do? So my question basically is, should a reparameterization of Mello's model become necessary to adapt it to perfect ranking scenario?
Yes, so perhaps it is possible for fixed value k.
Right.
Then the Mello's model actually, when parameter theta is, for example, less than 10, minus 10, then the corresponding error probability matrix is really close to the identity matrix. So instead of looking at the value of theta, the parameter, we can look at the error probability matrix and take some norm, for example, of the difference between the identity matrix and the corresponding error probability matrix. This is a simple way to solve this problem.
The last question. I have lots of lots of questions. I will write all of them in an email and send to you. I don't want to take too much of your time. So you have the right page in front of you.
Oh, okay.
In all these cases that you listed, your matrix Q, you see that there are two parameters. Of course, theta is minus half here, and 5 is corresponding to your choice that you made. One of the assumptions that underpins this particular model is the symmetry. The symmetry in the sense that the probability of you selecting the smallest as the true smallest and the probability of you selecting the true largest as the largest is equal.
Yes.
The 0.4287, 0.4287, and the same thing happens with other ranks.
Yeah.
So, is this a constraint on the choice of the model, or is there a way in which you can model it in such a way that you can create unequal probabilities for true selection?
Yes, so that depends on the choice of the distance, but but for the most commonly used distances, we have this kind of symmetry. So yes, even in some cases like Cayley distance and Hamming distance, we have a more constraint that this error probability matrix is just having two elements: diagonal value and off diagonal value.
Exactly.
And for Lie distance, actually, we have another symmetry in the matrix. So we have k minus 1 different values in each, k minus 1 over 2 different values in the whole matrix. So yes, no, oh yeah. So we have because the quantity, the elements, ijth element depends only on this quantity Cij, which is given here
based on a
from
distance.
the Lie distance. Yes.
Yeah. The other thing is more of a philosophical nature. If you have a multi-cycle sample, not necessarily a rank set sample,
Okay.
think of ranking in a general context and think of, for example, it could be a figure skating event in Olympics.
Okay.
And you have typically the number of judges in Olympics is an odd number, so that there are no ties. So 9 judges. And if K performers perform, they all have to rank them in addition to giving scores. Okay? So now, if you want, you can put perfect ranking in terms of agreement between the judges. So if all the judges agree perfectly, then you have a perfect ranking. Now, the question that I have of course, it may not be fair for me to ask you this question because I myself have done this before. Every time we define a ranking mismatch, not necessarily in rank set sampling, but in general, it is defined as a distance between 2 vectors. Right?
Yes.
You can look at your own definition.
Yes.
You have sigma I and pi I. And then you look at the distance between the vectors. But truly speaking, what you have is a matrix. Because if you think of sigma I and pi I, it corresponds to the ith judge. But if you have, for example, n judges, which corresponds to your number of cycles in the example of rank set sample. So, my question to you is, in this particular case, one has to take a spatial location in the matrix to define a norm. Is this something that you have given some thought? Is this something that is doable? Are there measures that are known as spatial distances that one could use in your context?
Yes, they can. We can. So basically, in what I understand is that our data is from complete rankings, and we can order them in a matrix, of course. And we should take something like the mean of these complete rankings, right? But the mean in the sense that we cannot take just the average, since if we take the average, we may go out of the integers. And
Correct.
So yeah, there are some distances. We can use some spatial distances. For example. I believe Spearman's rho and Spearman's foot rule are like that. So we can take like sum of distances, average sum of distances, like a measure of or the maximum of the all possible distances. Yes.
Correct. Yeah. Very nice. I have to say that your thesis, in my view, contains a great deal of original work with substantive results which are of high scientific level, and they have been presented in a clear and elegant manner. So, in my opinion, this thesis fulfills, in my view, all the conditions required for obtaining the PhD degree. So I am very satisfied with the thesis that you have produced.
Okay, thank you.
Thank you very much for including me in the presentation.
Okay, so
it is my turn now, who also has prepared a long report. I'll also be very brief. The conclusion of my assessment is that Nikolay I satisfies all the criterions for the awarding of a PhD title. The dissertation deals mostly and exclusively with different problems which involve the so-called Lie distance, which we can be thought of as the circular distance on a cyclic graph. And it was presented in the thesis that in certain cases it is better than the others because because of the specific metric which is on the circle, especially when we have some subgroups of experts that rank some samples, some objects, and they're in some sense some antagonists, or they have some competition between them. And in this sense, this metrics works fine. Also, the candidate was honest enough when it doesn't work better than the other metrics to write it clearly in the dissertation, which I think satisfies all the scientific honesty we have to maintain. Most of the results are correct and sound. The most non-trivial part for me is chapter number 5, whereby statistic, based of course on the Lie distance, on how to compare two samples, X and Y, so to say, and to test the hypothesis where their CDFs, their distribution functions, are equal, or one of the X or Y exceeds the other, for the award of PhD thesis. So we have to proceed now with the short reports. I would start with Professor Nikolov, who has been supervising his master's degree thesis, and I would invite her here so that Professor Balakrishna can listen to her comments in English. Yes.
Hi, Bala.
Hello.
Yeah, I know Nikolay very well. I'm sure that he is ready to work alone. So my conclusion is, the thesis represents a great deal of work. The results are well presented, and then their interpretation and application are at a high scientific level. In my opinion, the thesis of Nikolay I fulfills the conditions for gaining the PhD degree in probability and mathematical statistics. Therefore, I strongly recommend the thesis of receiving the degree of PhD.
Thank you to Professor Binkova, and I would invite the scientific supervisor of Nikolay I, Professor Stoimenova, to say her opinion about his work, very joint work.
I first should say that I was happy to work with Nikolay these 3 years of his study, and then we continue here in the Institute of Mathematics. So he works very hard and posed most of the problems in his thesis, and also he proved everything himself. So I'm satisfied with his hard work and his results, and I have my conclusion that he satisfies all the requirements of the law and the requirements of the Institute of Mathematics. What is not here is his ability to present his results. He presented in many conferences very well and have discussions with colleagues all over the world. He has 3 significant scientific awards in Bulgarian Academy of Sciences, and this means that he's one of the best PhD students here in the institute and probably in our division in the academy. So I'm fully satisfied by Nikolay's work, and I support his obtaining the PhD degree.
Thank you to Professor Stoyanova. And lastly, I will invite Professor Ignatov to say his opinion about the work and his conclusion about the work of Nikolay. So you confirm your positive opinion? Okay. So Professor Ignatov will read his conclusion in Bulgarian, but it is positive.
It's okay.
Given
So we would thank Professor Ignatov for his opinion. Now we'll continue with our next part of the Viva, which is basically open discussion with questions, speeches, or opinions about the work of Nikolay. If anybody has a question or wants to share an opinion, he or she can raise the hand and ask or just speak. The same applies, of course, to Professor Balakrishna. So if there are any questions or opinions that people would like to share, now is the moment.
I have nothing more to ask.
Okay, thank you. Any questions? So if there are no questions, I would like to ask Nikolay maybe to give his assessment as to in what scenarios because I'm probabilist, I have to say, and my understanding of statistics is limited. But reading the thesis, sometimes he says it works well, sometimes it works okay, something based on lead distance. And I would like to ask him first to give us his opinion. What is the overall merit of really of this lead distance? In which cases it is really strong, and in which cases it seems that it is really limited?
So, so to shortly answer that question, I should say that we should look maybe to the opposite ranking here based on lead distance and based on other commonly used distances. So we see that they quite differ from each other, and that is the main difference. So here is we can see that lead distance is works, let's say, better in situations where we have an antagonistic kind of rankings in, let's say, voting, where, for example, ordering in each group of is kept well. We take the more commonly used metrics. Here, the opposite ordering is the reversed one, which is not the scenarios in this kind of elections, let's say like that. So in general, the lead distance works well when there are two groups in our data, let's say it like that, and there are antagonistic groups. Okay.
So my next request to Nikolay maybe will be to present his responses to the queries by the scientific committee, because he has written an extensive list with comments, and regarding my concerns about some of the results, so maybe it is going to be good to comment how much the new requirement limits the application of the respective results, but I also know that he has responded to Professor Balakrishnan's several comments, so probably it would be good to display them. So that
Okay. So here are the response. So first I'll start with Professor Balakrishnan, since they're in this order in my presentation. So one of the questions was about the monotonicity of the variance of the random variable DL, and by following the sketch proof that he gave, it is quite straightforward to show that indeed the variance is monotonically increasing when n is greater than 3, and when the variance is equal when for DL when n is 2 and n is 3. So about the symmetry of the normalizing constant in Malus models. Okay. It can be shown that indeed when n is even we have this symmetric pattern for the normalizing constant. However, this is not true when n is odd, since the distribution of the random variable DL is not symmetric in this case, and therefore here these two probabilities, that DL equals n squared over 2 minus d, is not equal to the probability of DL to be just d. So this is not true when n is odd. However, the normal approximation used for constructing the approximation of this normalizing constant is symmetric for all n. So yes, in this case the approximation possesses this symmetric pattern for all values of n, while the actual normalizing constant possesses it only when n is even. Okay, the next one was about the R squared coefficient in the Malus model, and why it is equal to 0 when we have a uniform model. Basically, this coefficient is the ratio of the log likelihood ratio statistic and the total non-uniformity of the data. And even though if we assume that we have a uniform model, then we assume that our estimation of the parameter theta should be 0, and the total non-uniformity of the data could be 0, but it could be not equal to 0. Actually, it equals 0 only if n is a multiple of n factorial, and then the frequency of all permutations are n over n factorial. So for completeness, it is better to define R square in the following way, to include this case when the denominator is 0.
True.
For the 11th remark was about the confidence interval. Could we construct the confidence intervals about the estimated parameters? Yes, we can by some, for example, Monte Carlo simulation. But however, this will require a lot of computing resources. Yeah, so it is possible, but a more simple way is to just take the difference between the corresponding error probability matrices and take some norm for this difference. For example, P when P norm when P equals 1 or infinity. That's the maximal distance of the column or the row in a row. So they're the same in this case because they're symmetric matrices, and we see that this value 0.27, since it's a sum of probabilities, it's a significant difference between the two matrices. And about the critical comment for Professor Savov, yes, the proof of theorem 2.1 is incomplete because if we take the moment generating function about the random variable DL, the standardized random variable DL, then from the Hoeffding's theorem, it can be written in this form, where here f is a some kind of error or the difference to the normal to the moment generating function for the standard normal distribution. In a similar way, we can write the moment generating function for the random variable d tilde. So the proof is based on taking the ratio of the moment generating function of dl and dl tilde. So in order, the statement of the theorem is that this quantity mij equals so it equals this ratio, but in order the statement of the theorem is equivalent to the statement that this error here converges to 1 when n goes to infinity. However, this might not be true or is not proved, and one way to correct the theorem is to correct the statement of the theorem is to introduce some sequences of theta, not for a fixed parameter theta, that satisfy this condition. Here the power of n is from the powers of the order of the standard deviation of the random variable, and of course this result is weaker because for a fixed n we have a limit for the parameter theta that we can estimate in this way. Yes, so that's my response.
Are there any questions or comments further?
No.
Do you have comment, Professor Krishna?
No, I'm okay.
So maybe as a head of the jury and as somebody who has known Nikolay for some time, I'll allow myself to keep another 2 minutes to make a more general statement because I think it's important, and because I think at the end of PhD a student is really at the juncture of his career, and actually the decision he takes now is probably one of the most important if he is to continue in science.
True.
And I will say something from my experience because I think it illustrates best. I did my PhD in Manchester and I had the opportunity to work 1 year in France. And when I was in France with Jean Bertoine, I had the opportunity to go back to Manchester and a couple of other places. And of course, nostalgia or maybe the zone of comfort keeps you wanting to go back to Manchester. But Jean, who is also a close friend to my supervisor in Manchester, told me and told him, well, then must not go back to Manchester. Now is the time for him to learn new things and to expand his knowledge. And this is my honest opinion for everybody who completes a PhD. He or she has to take such a route which exposes him to challenging problems, to new material, because now is the time to learn. And friendship and other things with supervisors and area, especially, it's not about the supervisor, it's about the comfort zone where you're in. It's something that you know and you can do and repeat and repeat and repeat. Now is the easiest moment to break it. So I hope that Nikolay will take seriously a pause and think and choose the best for his career. And with this, I would like to conclude this part of the discussion. And now I would ask every member of the jury to confirm his opinion explicitly. So I would ask Professor Krishna to state explicitly whether he supports or he doesn't support the dissertation of the award of PhD of Nikolay.
I support it wholeheartedly.
Yes.
I have raised, as you pointed out, several questions and queries, and Nikolay's response letter has clarified all of them, and I am therefore quite satisfied in recommending this thesis for obtaining the PhD degree in probability theory and mathematical statistics at the Bulgarian Academy of Science.
Thank you very much. As also a writer of a long report, I also confirm my opinion that Nikolay satisfies all the criteria for the award of PhD thesis as assumed or as proposed by the Bulgarian Academy of Sciences. And now I would ask Professor Nikolov also.
Yes,
Professor Nikolov confirms,
yes,
and Professor Ignatov confirms. So the result of the voting is 5 yes for the award of PhD thesis, and no abstain and no against it. So with this, the viva of Nikolay is concluded, and he will be awarded the title PhD in probability and statistics. And if he wants to share some of his thoughts,
Thank you. So I would like to thank my supervisor, Professor Stuminova, for the support and the motivation during the years. I would also like to thank all the reviewers of my dissertation who take their work seriously, and I want to thank for their reviews. I would like to thank to my colleagues at the Institute of Mathematics and Informatics for being such nice friends, and of course, last but not least, to my family and my friends who supported me during my PhD program. Thank you.
Well done, Nikolay, well done.
Yes. So with this, the session is concluded. I would like to thank all the members of the committee and all people who attended in these circumstances the viva. With Professor Balkrishna, we have to be in contact with you to sign the respective documents and scan them at some point, but not now. And we'll be in touch. And we would like to thank you for your extensive work on this.
Thank you.
On this dissertation.
Congratulations, and good to see all of you in good shape. Thank you.
Thank you, Professor.
Okay. Bye-bye.
Bye-bye for now. Сега за само да кажа, че в 427 Николай донесен някои древни неща, който се чувства достатъчно сигурен да дойде за малко, да дойде.
С маска да яде.
Който се чувства способен.